Okay, so we're going to start module 2 today, which is beginning our discussion of soil and plant analysis. And we're going to start with soil sampling and excuse me, soil testing. So the basic idea here is that as we remove plants, whatever plants those are from the soil, those are going to have nutrients in them. And if we want to maintain the productivity of that soil, we have to replace those nutrients. And it is our job, your job as a producer, a manager, or a consultant to be sure that those nutrients are replaced to maintain the quality and productivity of soils. Right? It's just tragic that we would not. And that's our task. That's what this class is about. And so the first thing we have to talk about is getting a good sample. Right? You can't do anything unless you have a good sample. And when it comes to collecting a sample, there's no nice way to say this. You're the problem, right? The person collecting the sample is the problem. The computer science people have a phrase, garbage in, garbage out. And it's the same for soil testing. You can't do anything in the laboratory with a bad sample. And so it's absolutely imperative that the sample collected be representative of the area that you think it is. I hope that what you all aspire to do is to be the ones who design sampling plans and manage the people who collect those. Some days are nice to go collect soils. They aren't all. Some days it's hot. Some days the soils are too wet and they don't come out of the probe or the auger. Far better to be and also it doesn't take much education to do that. And thus it doesn't pay very well. You far better to be the person that designs it and manages the people who go do it. So you need to have the skill and the knowledge and the understanding to know what goes into a good sampling plan and understand what happens to that sample when it gets to the lab. And that's what we're going to talk about for the next couple of times. All right, so get a good sample. That's the bottom line. All right, so nothing magical can happen in the soil testing laboratory or any laboratory. Okay, you collect a bad sample, you're going to get bad results back, or they're not going to reflect what you think they're going to reflect, and you're going to make bad decisions. And if you make bad decisions, it's going to cost you money, or it's going to cost your company money, or it's going to cost your client money. And that's a recipe for disaster. And so I just want to give you a sense of the scale of what is happening here. Okay, so this is a picture of Mars. So as you know, there's a rover up there now trying to ascertain whatever rovers do. And so this just a giant landscape, right? And but you can imagine this is a field, and in your sample collection, you are going to collect maybe a gallon. Okay. Of that gallon, you're going to send in about a cup to the soil test lab. Of that cup, the soil test lab is going to analyze about a scoop. This is not the scoop they use. They use a different scoop. This is the scoop I use to make green tea. They have a different kind of scoop that's about the size of if you make coffee. It's about that size, slightly different shape, a very different shape. I'll show you something in a minute here, but this scoop has to represent this entire landscape. So if you mess up here, this little bit you're just doomed, right? So this part has to represent this. This part has to represent this, or this part is just always going to be a mess, right? And here's just some numbers to put that all into perspective. All right. So in general, right? So in general, a soil test is any chemical or physical measurement that you make on a soil. So if you want to measure texture, that's a soil test. You want to measure mercury in a soil, that's a soil test. However, when people talk about soil testing in the general public or even among soil scientists, they typically mean soil testing to make fertilizer recommendations. And depending on where you are, that could also mean salinity, where salinity issues are a concern. So for example, in the arid West, in Australia, in India, in Israel, for example, their soil test recommendations often come back with recommendations for how to manage soil soluble salts. And we'll talk about that later in the semester. We don't have those issues here. So our soil test lab doesn't make those recommendations unless you ask for it. Lately, more and more soil test labs have been asked to impart advice on whether there are elemental toxicity concerns. That's a new thing that soil test labs are being asked to do. Historically, it hasn't been something they have weighed in on, but as the urban gardening movement has grown, those urban garden soils are typically contaminated with metals of concern. And so they get asked to weigh in. They're, for the most part, poorly suited to make those determinations. We can talk about why that is later in the semester, or you can ask me during class and we can talk about it. The actual determination of the plant essential elements other than nitrogen are relatively straightforward. They're not difficult to do. What you really want from a soil testing lab is the interpretation and the recommendation. And those are difficult to do. And I know how university laboratories do it. I don't know how the private laboratories do it. University laboratories do it based on years and years and years of extensive and tedious field trials that have correlated fertilizer responses trials to soil test data, right? And so in my opinion, you can trust university soil test lab recommendations. I'm not saying you can't trust a private lab. I'm just saying I don't know how they make their recommendations. I don't know the basis for where they make their recommendations. If you have a good relationship with a private, so if you're a producer and you have a good relationship with a private lab, you should by all means continue to keep that relationship. But that's one that you have developed trust with over time because you have gotten good results for your particular operation. Okay. All right, so soil testing. So here's the idea, right? plants are only going to extract some fraction of the total amount of the nutrient that's in the soil. Okay. And so what we want to do is extract chemically, very quickly, that fraction, and then correlate that with the yield. That's the idea. The advantage is that we can do this well before it's time to plant, right? So we can do this now. If you can get a soil sample now while there's, excuse me, well, maybe not now, like as I speak, because it's like 20 degrees out and snow on the ground, but you get the idea. You can do it in the fall, and then when spring rolls around, you already know what fertilizers you need to apply, whether those be organic or inorganic, and you're ready to go. And so you can correct any problems, any fertility problems, before you have to even think about putting a seed in the ground. Okay. So the primary focus of soil testing has historically been phosphorus, calcium, magnesium, potassium, pH, and then corresponding to pH is the idea of a lime requirement, LR. Regionally, you may see issues with other secondary and micronutrients depending on the soils of that particular region. So some of the university and private laboratories know that their clientele have problems with, for example, sulfur or boron. And so they will offer packages that include those elements because they know that their people need those elements to make recommendations. And then some specialty growers like to have organic matter. And so our laboratory, the WVU Soil Testing Laboratory, will offer P, calcium, magnesium, K, pH, and lime requirement for free. You can pay for some of the micronutrients, not all of them. And organic matter you can also pay for. Every other state, so they'll offer it for free to anybody who lives in the state. If you have a West Virginia address, you can get free soil testing. Every other state charges anywhere from, last time I checked, which was about 8 years ago, it was anywhere from $15 to $45 per sample, except for Arkansas, where it was free for farmers, but everybody else had to pay. Organic matter is, we'll talk about how to measure organic matter when we get to the soil organic matter section. So I'll hold off on that for a moment. Unless you need organic matter for a certification purpose, specifically you want to be sort of certified organic, I'm not sure that it's worth getting. I helped Tom Bazin and Louis Jett, my colleagues and friends in Extension, give a high tunnel fertility workshop last year, and they got mad at me when I said that you shouldn't pay to get organic matter. And it's not that I don't think organic matter is important. I think it's critically important. I love soil organic matter. A major part of my research career is on soil organic matter. It's just that I don't know what you do with that number, right? We don't make a recommendation for it, right? So if it comes back at 2%, what do? Right? You try and make it better, right? But you already knew that, right? And so why pay the money for a number when you already know what you're going to do? You're going to try and do better. And so anyway, but if you just want to know the numbers so you can brag to your friends about what your organic matter content is, well, okay, I'm not going to stop you. All right, so soil testing objectives, right? So we want to accurately determine what your nutrient status is, and indicate how serious any deficiencies or excesses. Make a recommendation, and this is the part that is key. This is the hard part. And make an economic valuation of whether it's responsible, likely that you're going to get a response to applying that fertilizer. And then again, lately, they've been asked to make more, to weigh in on issues of potentially toxic elements. There it says heavy metals. I personally, it's the soil chemist in me, I don't like this idea of heavy metals. And there's only a few of the elements that people think are heavy that are actually heavy. It's better to call them potentially toxic elements. Anyway, but that's just a pet peeve. We all have them. That one's mine. All right. So how do you, what's the process? Well, first you have to collect a good sample. All right. And so here are the tools you can use. In the upper left-hand corner, we have an auger. Augers are great. They're kind of hard to work with, especially if you only want to take a very shallow sample, like if you're working in a pasture. They are good if you want to get down deep, no doubt about it. They have different kinds of bottoms here for different kinds of soils. So if you're sampling in wetland soils or sandy soils, you can get different kind of bottoms here. This is called a sharpshooter. It's really great for if you have to go down deep into soils. This is just a regular old garden shovel. They are terrible for collecting soil samples. And when you do your homework on soil sampling, you'll see a little bit why. They almost never go in vertically into the soil. They almost always go in at an angle. And when you do that, you overrepresent the surface of the soil. And many of the nutrients, because unless you're tilling the soil, they don't get equally distributed throughout the tillage zone, throughout the soil profile. And so you're going to get a bias sample. Excuse me. If you have to use a shovel, the video shows you the very tedious procedure that you have to use to use a shovel. My advice is don't use a shovel. Don't use this kind of shovel. They do make a ditch digger shovel that is more likely to dig straight down. It doesn't have the bent back that this one does. If you're just, a homeowner, you've got a few flower beds and a small garden, and you want to collect a sample to send in, a typical garden trowel is perfectly adequate. They do tend to be very straight backed, and so you can collect a decent, uniform, straight up and down kind of sample. This is the ultimate way to collect the soil sample, especially over large areas. And they come in different lengths. It's called a soil probe. They also make them with little handles on them so that you can eject the core that comes out directly into a bucket. I used to have some of those, but I loaned them out and they didn't come back. That's how much fun they are to use. You just sort of shoot a core into a bucket and go on with your day. So here's one in use. The tips are designed so that it doesn't compress the soil into the core so that it comes out easily. These are ATV mounted hydraulic cores. There's just basically one of these, but you don't have to actually do any physical labor except run the throttle on the ATV and push a button to push the probe down. Great if you have large areas, flat areas, ideally to sample, and money to burn on a ATV and hydraulic probe. Okay, So let's talk a little bit about how designing a sampling plan. And so here's something not unlike what we might see in grassland areas of grazing areas of West Virginia. And so what you want to do is what we call define your management zones, right? And a management zone is anything you or your client are willing to manage uniquely, right? So if you're willing to manage this little fenced in area differently than this fenced in area from this fenced in area, then you want to sample each of those differently. If you're not, collect one sample. Why might you want to do it differently? Because you want to maximize production on each of these. And these are clearly, well, to me, clearly, maybe not to you clearly, these are very different soils and they're going to have very different productivities, right? This is probably a stream running down here. And I hope you're not putting fertilizer down here in this waterway or letting your animals graze down here, okay? So anyway, a management zone is anything you are or your client is willing to manage uniquely. It's important to keep really good. To keep really good records, right? Because so this is a relatively, I don't know whether you would consider this a small garden or a large garden, but clearly somebody has applied, not uniformly to this entire area, some kind of organic amendment, right? Let's assume for fun that it's some animal-based manure, which we will learn by the end of this class has a lot of phosphorus and potassium. So that is not going to go away, right? And so, but at the next year when you come back, you may not have evidence. Maybe there's plants growing here and you're going to go want to sample this area. You may not be able to see evidence that this has this dark patch here. Maybe you will next year, but in 3 years, you're not going to see it. In 5 years, you're not going to see it. In 10 years, you're not going to see it. But that phosphorus is still going to be there, right? And so this is just a very, very small scale example of my attempt to impart upon you the importance of keeping good records. Because this is going to, if you take a sample here and expect it to represent this entire area, you're going to make a mistake, right? In this part of these unamended parts of the field garden are not going to get an adequate amount of fertility, applied fertility, right? So the other thing you want to think about, especially when you're sampling fields that have a history of animal use, is to exclude anything unusual. So animals are herding creatures, and so they tend to congregate, especially together and along fence lines. And this is probably either a watering trough or where they get fed. And so you can see they have torn up the ground right here. So you definitely don't want to sample this part of the soil, especially if you think it's going to represent this part of the pasture in the background here, right? So this would be an example of a place to exclude. We exclude fence lines, we exclude trees, tree lines, anywhere that doesn't represent the main area that you want to that you're going to represent. All right, and so then what you want to do, you've got the zone that you're willing to treat. You've got your management zone. Then you want to be sure within that zone, you're going to take a good representative sample. And there are a couple of ways you can do that. You don't want to just, right, so let's imagine there's a road that runs right along here. The easy thing to do is drive along this road, stop, hop out, bam, take a sample, hop back in your truck or car, drive down, hop, sample, get back in. Don't do that, right? What you want to do is zigzag your way down and then trudge all the way back. That's why you want to be the manager, not the sampler. And then that becomes your standard operating procedure. And you do that every single time. There's other ways to do it. You can start somewhere and, zigzag your way around, and then you finish and then come back. They have these crisscross patterns. As long as you're doing the same thing every year, your data will be comparable year after year after year. We're in West Virginia. We rarely have these sort of nice Pythagoras-based shapes. We have something that looks more like this, right? But the same principles are at stake, right? And so sometimes these are called drunken sailor sampling plans, where you just sort of wander around and depending on the size of the field, every 10, 20 steps, you put your probe down and collect a sample. So this is a management zone, this is a management zone, and this is something you're going to exclude. This is the management zone because it's on the other side of the fence. This is another management zone because it's on the hillside, right? But the idea is, this is your standard operating procedure. This is what you're going to do every single year. And it gets written down and it gets put in your, what we're, by the end of the class, going to call your nutrient management plan, okay? Anybody who works for you follows that plan. Everybody, no matter what. There's another, as technology improves, both for, in all senses of the word, right? We're doing more and more precision-based sampling and agriculture, right? And so it used to be very, very difficult to know where you were in space and time. Now your cell phone company knows where you are all the time, right? And so you can, with very, very inexpensive equipment, plot your position in a field. And so here, just because it was easier, I've shown a rectangular field, but you got all these points, right? And so you can sample at these points. Excuse me. And when you send those and get your data back, you get, instead of one number for an entire field, like you might have here, right? So when you sample like this, you're going to get one number for potassium, right, for this field, and one number for potassium for this field, and one for this field, and one for this field. Now what we get is high potassium in this part of the field, medium potassium in this part, in this part of the field, low and very low, right? And so now we can start to make much more precise potassium applications and start to smooth out where our soil test levels are, and hopefully smooth out our yields across the field. Right? And then we're following that up with not only tractor-based and satellite-based imagery of what those yields are, but even in some cases, drone-based technologies to sample, to monitor those yields. And so these farmers have these extremely expensive tractors and are getting back yield data as they drive, overlaid with their soil test data, right? And so they're just getting incredibly precise data on how to manage nutrients, in some cases water, in some cases their pest management, and just the ability to integrate that with satellite data. If you're interested in this kind of thing, Dr. Pena is doing enormous important work in this realm. All right, and so just more kind of precision sampling plans. One of the things that's been shown to by a colleague in Extension County agent in one of the eastern Panhandle counties is we're getting she found really good responses to what's called variable rate liming, right? And so you do high precision sampling, and you don't apply the same amount of lime to the entire field. You focus that lime only where you have the lowest soil pHs, right? So up here, down here, and it pays off, right? And it pays off. Okay. Well, I want to show you. I don't know how many of you have ever soil sampled in West Virginia, but sometimes it's a very difficult thing to do. Let me show you this little clip of them soil sampling grasslands in Ireland, only because they have this really cool soil sampler.
The new fiber internet source is here. Wow, we're Breezeline, your delivery service provider. And no matter your business, we got you. From the steadily creating spreadsheet update to the tech making mode we're fast.
Hello, my name is Declan McCarter. I'm an equine specialist with Charters. I'm here today with my colleague Mark Croker, who's a nutrition specialist based in downtown Catholic. I'm here today to discuss the importance of taking a soil sample and how this information should be utilized with regards to our soil fertility program. Mark, maybe just explain to us why it's important to take a soil sample.
Okay, then soil testing is the first step in terms of managing soil fertility. It gives us a baseline as regards the soil nutrient status, whether it's very low, medium, or very high. This allows us to prepare a fertilizer plan and plan line application, organic manure applications, and fertilizer applications.
I don't expect this could save the farmer money if the soil fertility is setting is quite high. That will influence what the price is high and potentially save money. Or if the soil fertility is very low, the grass on production is clear to help you maximize gas output.
Correct. It really gives the farmer the information for their own field on how to manage both nitrogen, phosphorus, potassium as efficiently as possible. They're allowed to target organic manure to fields that are low in fertility, that come back in the Southwest report. It will also allow us to put a lining program in place and target different parts of the farmer's line that goes up to the optimum soil pH. But as I say, getting the soil sample is probably the most important thing. It's very, very important to be organised and prepared. And for example, what we use mainly in this country is a funnel type of auger. Yeah. And it's a 4-inch core. It's a conical shape, it's narrow in the base and wider in the top. And this allows the soil to move up in the core. Now we must get a 4-inch core every time. Also, it's important to have a soil mapping plan. So again, I have mapped out the farm here in Johnstown to show us the areas that need to be soil sampled. So that's very, very useful. So like we generally take a sample every 2 to 4 hectares. Also, how we use that is we use soil sample boxes, and again, we label these appropriately with a black column marker.
Very good. So this is a very organized map. This is what your map here. We've identified the different areas. That's good. Have your maximum set, hectares per sample?
Well, generally, we take a sample every 2 to 4 hectares, and they're managing blocks. And again, like, you know, it's the way we manage them in terms of NPK and line applications.
So Mark, if you look at this product here, and you can see the products around it, they're divided.
That's right.
So, can you explain your thing with your soil over? How would you proceed with taking a sample from the field?
Okay, well, first Declan, we divide any unusual spots in the field, around gateways, where maybe, you know, around headlands, where animals have congregated around the feeder, all those, any unusual spots are divided.
Any of those, like you post them.
Yes, line down give an abnormal result. So we're looking for a representative size sample. That's very, very important. So we're staying well out in the field. We will walk in a double-shaped pattern to get our representative sample, and we're taking 5 cores, 5 side cores. This will be dipped into the ground 5 times on each leg of the core. Now we recommend taking a minimum of 20 side cores per size sample. So that will give us enough soil that will be delivered to the lab for analysis.
And when you need to look at the box that you put us in that lab, and we're currently saying we're going to take a random sample of those 20 cores. Yes, in that box.
All we'll do, we take 20 cores, we will sub-sample our 20 cores. This box will hold 15 cores. Yeah, we'll fill the box and completely, that will be sent off to the lab for analysis, and we'll get our results back.
So this is to highlight the quickly you've got a big farm in large size samples, but you clearly identify a market.
Yes,
Which paddock this sample is for.
yes. That's why it's very important to say you have to map there that, you know, we have the samples will be numbered, and also we have a field name for each field as well. So when the information comes back, that the farmer and yourself can relate, you know, to what parts of the farm it is, and that is very, very important that you have a plan or a numbering system in place there.
And so just go back to the soil iron, you mentioned it's very important that you like to get on the same amount.
Yes, the size sampling depth is very, very important, Declan. I say we're looking for a good core each time. We're looking for a 4-inch core. So we're looking for 20 of these into the side core. That's going to give us a good guide as regards nutrient value. It's most important as regards phosphorus, because phosphorus tends to be in the top few centimeters of the soil. If we take shallow side cores, and maybe if the soil is too very, very wet or too dry, then we will get a false reading for phosphorus. So it's very, very important that we get the full 4-inch core at a time, because we are basing our advice for the next 3 to 5 years on this soil sample.
Very good. I suppose, Mark, what are the optimal time for the soil sample here?
The optimum time is generally September to March. But we generally like to have a minimum of 3 to 4 months since.
Okay. So basically, he's just said the same things I did, just in maybe a better accent. I don't know. I did want you to see how easy that probe went in. And he sort of emphasized, again, some of the things that I said. After you collect your samples, they then go to the soil test laboratory. Our class is too big to walk you through ours. So we have this video, walk you through the Iowa State Laboratory. And I'll pause occasionally to point out some different things, Verbo.
The thing that's different about a Verbo vacation home, you always have the whole place to listen.
Soil testing is a valuable diagnostic tool for growers. Soil testing laboratories, such as at Iowa State University, often evaluate soils for their available nutrient status, organic matter content, pH, and lime requirement. The first step in the process is to ensure that a proper soil sample is obtained. Most soil testing laboratories have printed materials on how to obtain a good representative soil sample. After the sample has been received, the laboratory will follow these steps in handling the sample. Receiving and recording the sample, drying, grinding, extraction, measurement, interpretation of the results. When handling thousands of samples, keeping careful records is imperative. Each sample received by the Iowa Soil and Plant Analysis Laboratory is assigned a unique number that follows that sample throughout each operation. Soils collected in the field vary in moisture content. In the past, analysis was performed on dry soils for major soil nutrient determinations. However, recent research has indicated that the soil test potassium values from a moist sample analysis correlates better with yield response for corn and soybean. Iowa State offers interpretation of potassium for both dried and moist samples. Most analyses, such as pH, lime requirement, or
So Iowa State is the only state in the country that I'm aware of that uses moist samples for any kind of soil determination. Everybody else that uses dry soils.
organic matter and micronutrients require the sample to be dry. Each sample is maintained in its own bag with its unique laboratory number. The drying usually takes about 16 to 20 hours at 40 degrees Celsius. Once the samples are dry, they are ground to pass a 2 mm sieve. For some tests, finer grinding of samples is necessary. Laboratories use 1 to 10 grams of soil for nutrient determinations, so it is important that the soil be uniformly mixed and that the small subsample is representative of the large sample. For determination of potassium using moist sample analysis, the samples are homogenized and sieved to pass a 1/4 inch sieve. The moisture content of the sample is then determined by drying the samples at 105 degrees Celsius in a drying oven, and weighing is based on the dry weight equivalent. After the sample is dried and ground, it is ready for extraction.
That's the scoop right there. So I showed you my wooden green tea scoop when we were looking at the picture of Mars and the milk gallon jug and my Batman coffee cup. That's the actual scoop.
Action of the nutrients. The first step is to obtain a specific quantity of soil. Most laboratories do this by volume as shown here. Different size scoops are used for different analyses. The scoop is placed into the dry ground soil. The scoop is tapped 3 times to settle the soil, and then the top of the scoop is leveled. The choice of extractant to be used is based on the test being conducted. A soil testing laboratory does not measure the total of plant nutrients, but rather estimates the plant available nutrients. Thus, a chemical or mixture of several chemicals is used to approximate what is available to the plants throughout the growing season. Based on different soil properties, crops, and weather, it is not surprising to learn that different labs use different chemicals. Also, different laboratories have different procedures to determine soil organic matter, different soil to water ratios in determining soil pH, and different means of determining lime requirements.
So for the most part, you don't have any control over what soil extractants are used by the lab. That's all been chosen for you. And at university labs, those were decided many, many years ago based on the common soils in that state. And the extractants that are used in the humid East are very, very different than the extractants that are used in the arid West, or that are used in Hawaii or Puerto Rico or Alaska for that matter.
Based on soil properties and other tests to be run, labs may use more than one extractant. For example, Iowa State has 3 different phosphorus tests that it uses. The test methods used at Iowa Soil and Plant Analysis Laboratory have been field calibrated with crops grown in Iowa soils under Iowa climatic conditions. Iowa State lab procedure includes a control sample with known values of the components being analyzed in every tray of 10 unknown samples. Here, the known control sample is being added to the extraction container. It will follow all the steps of the unknowns. If the soil test values of the control sample are not within quality control limits, the unknown samples will be reanalyzed. The common extractants or methods used at Iowa State for soil fertility analyses are shown here. The test for pH uses a 1-to-1 soil to water ratio. The test for lime requirement uses the Sikora method. The test for organic matter content uses dry combustion. The test for phosphorus may use the Melic 3, the Bray 1, or the Olson method. The test for potassium may use ammonium acetate or Melic 3. The test for zinc uses diamine triethylene pentaacetic acid, commonly known as DTPA. The laboratory can determine many other elements, including nitrate nitrogen, using the potassium chloride extraction method for late spring nitrate test and end of season stalk nitrate test. Sample extractants need an opportunity to react with the soil. Here, samples are being placed on a shaker for a specific time period. And here, the samples are being filtered. After filtering, the extracted nutrients can be measured. Even though different equipment may be used in different soil testing laboratories to measure available nutrients, it is the extracting solution that normally determines nutrient availability and not the equipment used to make.
So that's a really important point, right? And that's why you can buy home fertility kits in the back of most garden catalogs. And they will give you a number for P, calcium, magnesium. Those numbers are fine, right? Especially if all you want to do is compare year to year to year, because it's not the instrument, it's the recommendation that comes later that's much, much harder to do.
The measurements. Soil testing laboratories use expensive equipment for analyzing soils. Some of the instruments used at Iowa State and their operating principles will be discussed. After mixing and equilibrating the soil with water, a pH electrode is placed into the soil suspension. The electrode is adjusted to read pH 4 and 7 with standard buffered solutions. The potential of the hydrogen ion activity, known as pH, is measured across a glass membrane and translated to an electrical potential, indicating the pH of the solution. For lime requirement tests, a buffered solution is added to the soil-water mixture and equilibrated after pH determination. The buffered solution removes the potential acidic ions from the cation exchange sites into the solution, where the pH electrode measures their activity. The decrease in the buffer pH relates to the quantity of lime required to raise the soil pH to 6.0, 6.5, or 6.9. A colorimetric technique is often used for phosphorus determination. The extracted sample solution is mixed with a coloring reagent, acid ammonium molybdate, and a reducing compound, ascorbic acid. The coloring reagent and the reducing compound combine with phosphorus in the sample solution to form phosphoammonium molybdate complex that is blue in color. The intensity of the blue color in the complex is proportional to the concentration of phosphorus in the solution.
So let me stop right here. So that method measures actually the dissolved orthophosphate anion, PO4 superscript 3 minus. Not total phosphorus, like another instrument that's going to show up here in a minute.
Organic nitrate and ammonium nitrogen in solution is also determined colorimetrically. Iowa State uses a Latchik automated flow injection analyzer, the instrument shown here, for this determination. A peristaltic pump is used to aspirate sample and various reagents into the manifold and mix them before passing the colored product into a flow cell for measurement. Again, the intensity of the color developed is measured as absorbance and is linearly proportional to the concentrations of nitrate and ammonium nitrogen in the standards. An atomic absorption spectrometer is often used to determine potassium and can be used for other cations as well. In this procedure, a solution containing potassium is passed into a flame. The potassium
So you may have used or seen demonstrated an atomic absorption spectrometer in your general chemistry lab. Very few soil testing laboratories still use AA because they're just slower. And the linear range, that is, the concentrations that you can measure are just not as good as the instruments that are going to come up here in just a minute. I'm actually kind of shocked that they still use this. And I think it's because it's an older video. They almost certainly have gone to ICP, which is the instrument right after this one.
atoms in the sample solution are raised to a higher energy state in the flame. As they cool, they fall back to their unexcited or ground energy state and emit a specific wavelength of light. That is 766.49 nanometers, which is then measured. The intensity of the light is directly proportional to the concentration of potassium in the sample. The most expensive analytical instrument in the laboratory is the inductively coupled plasma atomic emission spectrophotometer, or ICP-AES unit. The operation is complex, but basically involves ionizing the sample ions by extreme heat through electromagnetic induction in an inert gas. The principle of this process is that each element emits energy at specific wavelengths peculiar to its.
So see that blue bit right there? That's a plasma. It operates in a similar way as the flame in the AA. But because it's like 13,000 Kelvin, 16,000 Kelvin instead of 4,000 Kelvin like a flame, it just is much, much more efficient at ionizing all of the elements. The other problem with the AA is that you need a different lamp for every single element that you want to analyze. So you have to do all of your potassiums, all of your calciums, and then you do all of your potassiums, you change your lamp, you do all of your calciums, change your lamp, do all of your aluminums, change your lamp, do all of your magnesium. So it just takes all day. Whereas the ICP does all of these at the same time. And then the linear range. So for example, on potassium, the linear range on an AA is probably 0 to maybe 50 parts per million. Whereas on an ICP, the linear range for potassium is probably 0 to 10,000 parts per million. So you can just analyze a much larger range of samples.
Atomic character. The intensity of the energy emitted at the chosen wavelength is proportional to the amount, that is, the concentration, of that element in the sample being analyzed. Thus, by determining which wavelengths are emitted by a sample and by determining the intensities of those wavelengths, the elements can be qualitatively and quantitatively determined from the given sample relative to a calibration standard. The ICP instrument is quite sensitive to element concentrations and can measure both metals and nonmetals simultaneously. It is often the unit of choice when multiple analyses are wanted from the same sample. All Iowa State interpretive data can be found in PM 1688. Many other states have similar publications. The values obtained in the laboratory for plant available nutrients should be thought of as indices, which mean little without proper interpretation. Interpretation is specific, wanted from the same
So I
sample.
want to.
All Iowa State interpretive data quite sensitive to element concentrations.
Let me back up here.
and
I'm
can
sorry, I
measure
missed a
both metals
pause.
and non-metals simultaneously.
So you remember how I said that more and more labs are being asked to make recommendations on potentially toxic elements. So I pause at the wrong place. The nice thing about the ICP, especially the newer instruments, is that they analyze, they'll give you peaks for all of the elements that are in your sample, even if you didn't know they were there. And so let me go forward just a second here.
It is often the unit of choice when
So
multiple.
that one right there. Oops, so there's selenium, right? If you didn't know selenium was in your sample, all of a sudden now you do. You didn't necessarily calibrate for it, but
Quite sensitive
but
to
that if you
all
wanted to, you could go
conditions.
back and get it. Let me see if I can catch it again. So there's cadmium, right? You didn't know cadmium was in your sample, but now you do. And if you want to know how much, you can go back and take that sample and develop your standards for it. And now you know that there's how much cadmium is in your sample. Let me see if I can catch another one. It goes really
Non-metals
fast.
simultaneously. It is often the unit of choice.
That one is antimony, right? Antimony. That's that one is very toxic, shows up as gunpowder residues,
When multiple analyses. are
Tellurium,
rendered from the same sample.
tungsten. So
All ionospheric interpretive data can be found in PM 1688.
again, with more advanced technologies, we're able to make better, we're able to do better things for people that rely on soil test laboratories. Now, having said that, there is a caveat, and that is that the extractants that soil test laboratories use are not always ideal for the potentially toxic elements of concern, right? And so so just because you've pulled it out with one of the extractants doesn't mean that it's not there, right? And so that, I guess what I'm trying to say is the methods that EPA uses to decide whether something needs to be remediated are not the methods that a soil test laboratory would use to decide whether something is potentially plant available. Okay, let's keep going. All right, and so one of the things that I talked to you about was that this idea that as technology improves, we're going to be moving, in my opinion, we're going to be moving from, we're going to be taking instruments to the field rather than bringing samples to the lab. And I want to start introducing you to some of them that I have, both to pique your interest in those and to alert you to what's coming down the road, and in case you want to use them for your projects. So this is a chlorophyll meter, and I have this one, and you are absolutely welcome to use it. And so it just measures chlorophyll concentrations, and it has built-in calibrations for a variety of crops. I don't necessarily know if I have it for the crop that you're using, but I'm certainly willing to give it a go. This is another app-based thing. So what you do is it comes with this board. It's like an aluminum sheet. And so you take a picture of your leaf on some sort of standard background. And then based on this yellow and green color, you get an indication of how green your leaf is, which is an indication of chlorophyll content, which is an indication of nitrogen status. All right. And so then there's this question of how do we extract the nutrients, right? And so here's the rough, sort of very unmathematical relationship. We've got nutrients on a solid that we have to get into solution, that we have to get to the root surface, that once they're on the root surface, they make their way into the plant tissue, right? And so, and then here's the sort of the definition of all those pools, if you will. All right. So any soil testing program is only as good as the quality of the supporting research. So I mentioned earlier that I know, well, not personally know, but they're my colleagues, many of them who have passed on to their greater reward. The people who have made their careers doing those early yield trials, fertilizer yield trials, on how to go from a soil test value to a, let me put myself back on the screen so I can talk with my hands. How to go from a soil test value to a fertilizer recommendation. I know across the country, the people who worked so very, very hard to make that happen. They committed their lives, they committed their careers to making that happen, right? And here are the steps. You have to determine what are the forms of the available nutrients in the soils in that area. And it's different, right? The form, and we'll talk about this as we move through the class. And then you have to find the extractants that are suitable for those forms in those soils. And then we have to identify the productive capacity of those soils, right? And we talked about that a little bit, actually in class last time. And then we have to, this is the hard part, right? The response trials. And so many graduate students paid their way through school doing these kinds of fertilizer response trials. And then we have to establish these protocols, right? And it's hard, difficult work, but it was done so that we can make competent field recommendation, competent fertilizer recommendations for producers in our state, right? And so here's the idea, right? And this is really hard to grasp. And this is not my figure. I went to a webinar and swiped their slides for you. Committed a crime for you. So the growing season is, let's say, 120 days, right? The extraction that happens in the field, in the laboratory, is maybe 5 minutes. The extraction that occurs in the field is, 120 days converted to minutes, 200,000 minutes, give or take, right? So what we really need to do, what we're really talking about is just, if we think about the growing season as a movie, but just one little snippet out of that whole reel of film, right? And so this picture is mine, right? I did make this picture. And so we're going to imagine that this whole brown slide is the soil. And we're going to evaluate extractant green and extractant yellow and extractant blue. And the question is, which is the best extractant? And the answer is, you actually don't know. Just looking at this, you might be tempted to say it's extractant green because it's extracting more. But you can't actually know which one is extracting, which one is the best, until you correlate it with yield, right? And so the best extractant is the one that is, when we put each of our soils in a soil test category, low, very low, up to very high, and then we extract those and then see which one is correlated with yield, that's the best extractant. And so this could be the yellow one, right? And this could be the green one. Until you do that field experiment, you just don't know. You just don't know. And then how do we know how much fertilizer to apply? Again, you don't know until you do the field experiment where you put on fertilizer at different rates and see how likely you are to get a response. So here are the Iowa State video talked about all the different extractants they use, right? And so here, just in the Northeast, are some of the ones that we use, right? And so New York uses something called Morgan. Morgan was an old soil chemist, and then Maine and Massachusetts modified Morgan. There's a Malic 1 extract, there's a Malic 3 extract. The actual details of the extractants are not what is important, because there are lots of them, right? Here's what the composition is. If you go to the courses resources section, there's a one of the documents has this table in it, in the appendix. It's all of them that it's all of the extractants that are used in the Northeast, and I just made this table out of that, summarizing them all. And all the methods that they use. Right? And but so there's a lot, right? There's a lot. And so part of what I want to get across to you is that when you send your sample to, we don't get this response anymore, but we used to get it a lot. Soil testing is free if you're a West Virginia resident. I'm sorry, if you're a West Virginia, if you have a West Virginia address. And so people would say, I sent my sample to you and I got one number. I paid to send it to A&L Laboratories or Dairy One or whatever, and we got different numbers. The one I paid for must be right because I paid for it. And the question you have to ask yourself is not what's the number, right? Is what's the recommendation? Because the number is going to depend on what extractant they used. So let's look at the macronutrients, right? So if they used modified Morgan and we're using Malic 3, you're going to get a different number. And this is my way to try and describe that to you. What's the difference between Celsius and Fahrenheit? If you told me your temperature was 50, I wouldn't have any way of saying whether you were dead or alive, right? Because if your temperature is 50 degrees C, holy smokes, that's a problem. You're dead. But if your temperature is 50 degrees Fahrenheit, well, I mean, that's not good, but at least you're not dead. And it's the same way with the different extractants, right? Depending on which extractant you get, it means different things. And so you cannot compare extractants. And so the first question you have to ask yourself is, if you get 2 lab reports from 2 different laboratories, did they use the same extractant? If they didn't, then just stop. Just stop trying to beat your head against the wall and figure out why. There are, if you want to make yourself crazy, you can go to the literature and try and find correlations between the two and make that algebraic substitution and see if they agree. But why? Because the number that comes out on a soil test report is not important. And we'll talk about that more next time. What matters is the recommendation. Okay, I hope I made that clear. All right, so the only reason that number matters is because we want to put you into one of these soil test categories, right? So that number comes out of the ICP as this is a quantitative number, but it puts you into one of these categories. And then from this category, we then turn around and make a fertilizer recommendation. We're going to talk more about that in detail next time. And then this is how that's done. These extensive field trials that are done plot by plot by plot, harvested by hand, sometimes with small plot machinery. But then the idea is, for each of these, we're going to add different amounts of fertilizer. We're going to go to a field that has a low soil test potassium number, a medium soil test potassium number, a high soil test potassium number, and we're going to get these yield curves, right? And then we're going to convert each of these to a recommendation for every single crop, right? So I want to emphasize again that soil test labs can determine nitrate, but they don't, because nitrogen undergoes too many changes microbiologically. The only reason they do determine nitrogen is because for something called the pre-sidedress nitrogen test. And there's a extension bulletin in the courses resources section that you can read if you're interested in that. We don't have those for all crops. In fact, I'm only aware that we have it for corn. And then there's another one called the late season stock nitrate test. There's also an extension bulletin on that in the courses resources section if you're interested. So the pre-sidedress is a soil test. The stock one is a plant test. So again, I just want to talk to you a little bit about in-field measurements. So again, this is a portable XRF unit. I actually own this one. Unfortunately, I can't let you use this one because it generates gamma rays that you can potentially expose yourself to. If you want to come back as a graduate student, we can talk about that. But the idea here is that you can take this to the field and make measurements on the ground for soils, plants. I had a graduate student do it for manures and forages. And you can just take way more samples in the field than you can for than if you had to, probe and composite and then bring them back to the lab. This is the one I can let you use for your projects. In fact, those of you who are doing XRF-based projects, it's the one you will use, because when we close the lid, no X-rays come out. You are going to have to take a safety training, but it's entirely safe. I've had it tested several times. Once the lid is closed, no X-rays escape, so you're 100% safe. I don't have this, though I wish I did. It's called Visible NIR. It can identify soil organic matter. Here they're using it to identify microbial biomass and diversity. So anyway, there's just so much happening. It's a great time to be technologically aware. Just a lot's happening on the technology front and in agriculture. All right, that's the end of today.